NASA says its Voyager 1 probe, the most distant human-made object in the universe, is sending usable information to Earth again after months of spouting gibberish.
We thought we understood the shape of our solar system. We mapped the planets, we named the moons, and we believed that once you passed Pluto, there was only empty darkness stretching endlessly into the galaxy. But then Voyager 2, a small spacecraft launched in the late 1970s, slipped across the edge of the sun's influence, and what it detected stunned everyone back on Earth. Its instruments recorded a sudden silence where solar plasma had always flowed. Charged particles shifted in ways no scientist had expected. A strange magnetic ripple appeared, as if an unseen boundary had just been crossed. It was almost as though our entire solar system wasn't drifting freely in space at all, but sealed inside a massive invisible bubble. Was this boundary a natural shield formed by our star? Was it a cosmic wall, holding us inside? Or, unsettling as it might sound, could it even be something artificial? Something watching us? The signals Voyager 2 sent back raised more questions than answers, and they forced scientists to rethink everything they thought they knew about the very limits of our cosmic neighborhood. To truly understand how remarkable this discovery was, we have to rewind the story. We have to go back to the year 1977, a time when Earth itself was in turmoil. It was the height of the Cold War. Technology was racing forward, and humanity was reaching for the stars in ways it never had before. That summer, NASA prepared to send a pair of spacecraft farther than anything had ever traveled. These weren't missions that would simply orbit a planet or take a few pictures. They were designed as interstellar explorers, machines meant to travel through the outer solar system, slingshot past the giant planets, and then, if all went well, continue sailing into the uncharted darkness between the stars. These two probes would become known as Voyager 1 and Voyager 2, and they would change our understanding of space forever. Voyager 2 was launched first on August 20th, 1977, riding a Titan IIIe rocket from Cape Canaveral, Florida. Just a couple of weeks later, on September 5th, its twin, Voyager 1, followed, hurled into the sky aboard another massive Titan rocket. The numbering might seem confusing. Voyager 2 left Earth before Voyager 1, but the names weren't about who launched first. They were about who would reach Jupiter first, and Voyager 1's trajectory meant it would arrive at the giant planet quicker. Together, these twin spacecraft carried the hopes of an entire generation of scientists. They were humanity's messengers to the outer planets and beyond them, perhaps to the stars themselves. But why send two nearly identical spacecraft? The answer lay in a rare celestial opportunity. In the late 1970s, the four outer planets, Jupiter, Saturn, Uranus, and Neptune, were lined up in just the right way that a spacecraft could use their gravity like stepping stones. By flying close to one giant, the probe could slingshot around it, gaining speed and adjusting its course, then fling itself toward the next planet in line. This was called a grand tour, and it was something that only happened about once every 176 years. If NASA didn't launch in that exact window, they would have to wait until the 22nd century to try again. The stakes couldn't have been higher. This was humanity's one shot, at least in our lifetimes, to see all four of the giant planets up close. Each Voyager probe was a marvel of 1970s engineering, designed to survive in the most hostile environments imaginable. Both were equipped with gold-plated copper phonograph records, now legendary, the so-called golden records, that carried sounds and images of Earth, greetings in dozens of languages, music from around the world, and even recordings of a mother's kiss and a child's laughter. If some distant intelligence ever found one of these probes drifting through space, the golden record was meant to tell them who we are. But beyond this poetic gesture, the spacecraft themselves had a much more practical mission. They were equipped with cameras, spectrometers, magnetometers, plasma detectors, and cosmic ray instruments. Everything needed to peel back the mysteries of the outer planets and the space beyond them. For scientists in the 1970s, much of the solar system was still a blur. We had fuzzy telescope images of Jupiter and Saturn, but very little detail. Uranus and Neptune were little more than distant green-blue dots. No spacecraft had ever ventured past Mars except for the Pioneer probes, and even those had only skimmed Jupiter and Saturn without the technology to reveal much detail. The Voyagers promised something revolutionary, not just glimpses, but close-up encounters. Flybys that would map planets, moons, rings, and magnetic fields in a way no one had ever seen before. Voyager 1's path was designed for speed and precision. It would fly by Jupiter, then Saturn, and then swing upward out of the plane of the solar system, never to return. Voyager 2's trajectory was more ambitious. It would take the long road, visiting all 4 outer planets, Jupiter, Saturn, Uranus, and Neptune, before heading outward into interstellar space. Together, these 2 machines would give us the most complete picture of the outer solar system ever assembled. And as we'll see, the surprises they uncovered went far beyond anything even the boldest scientists had dared to predict. At the time of their launch, nobody knew how long the Voyagers would last. Their power came from radioisotope thermoelectric generators, nuclear batteries that slowly converted the heat of decaying plutonium into electricity. Designed to last maybe 5 years, possibly 10, nobody realistically thought they'd still be running decades later. But the Voyagers proved tougher than anyone imagined. They became not just scientific instruments, but legends, tiny human outposts in the void, still calling home long after the engineers who built them retired. But before they could reach the edge of the sun's domain and encounter that mysterious bubble that so baffled scientists, the Voyagers first had to complete their original mission, to journey past the gas giants and send back humanity's first close-up portraits of these distant worlds. And so, after their historic launches in 1977, the countdown began for their encounters with Jupiter, the king of the planets, a world so massive it could swallow all the others combined. Nobody knew exactly what they would find. Nobody expected what came next. When the Voyagers left Earth, they weren't just blind messengers sailing into the dark. Each one carried a carefully chosen set of instruments, the best technology 1970s engineering could provide, designed to sense the invisible and reveal the unknown. For NASA, the goal wasn't simply to fly past a few planets and snap photos. It was to gather the kind of hard scientific data that could rewrite textbooks for decades to come. And for that, the spacecraft had to be packed with tools capable of seeing the universe in ways human eyes could never manage. Both Voyagers were equipped with imaging systems, cameras that could capture not only visible light but also filter and measure colors and wavelengths that would highlight chemical differences in clouds and surfaces. These cameras, paired with long focal-length lenses, would give us the first close-up portraits of the giant planets and their moons. But seeing wasn't enough. The probes needed to taste, to measure, to listen. They carried spectrometers, devices that broke down light into its component wavelengths, allowing scientists to determine what atmospheres were made of, what gases swirled in clouds, and even how energy was balanced across an entire planet. Then came the magnetometers, sensitive devices that could detect invisible magnetic fields. The protective shields planets generate deep inside their cores. These fields trap particles, form belts of radiation, and in some cases create auroras, dazzling light shows at the poles. Until Voyager, no one knew how intense or how complex these fields might be. To measure them directly was like lifting a curtain on an unseen layer of reality. Alongside these, plasma detectors and cosmic ray instruments were installed to record the behavior of charged particles. These devices would be especially important later, as the probes neared the edge of the sun's influence, where the solar wind gives way to the cosmic winds of the galaxy. Every instrument played a role, like pieces of a puzzle scattered across the void. But collecting data was only half the battle. Getting that data back to Earth was a feat of its own. Imagine a spacecraft the size of a small car, powered by less than 400 watts, about as much as a household microwave, and transmitting signals across billions of kilometers. By the time Voyager's whispers reached Earth, they were fainter than the static of a TV left on an empty channel. To catch those signals, NASA relied on the Deep Space Network, a trio of massive antenna arrays positioned strategically across the globe. One in Goldstone, California, one near Madrid, Spain, one near Canberra, Australia, each separated by 120 degrees of longitude so that no matter where the Earth rotated, at least one was always listening. These weren't ordinary antennas. Some were 70 meters across, giant dishes capable of scooping up the faintest whispers from the edge of the solar system. And they didn't just listen, they spoke. Commands from Earth, coded in binary, were beamed upward, telling the spacecraft when to turn, what instruments to activate, and when to send back stored data. It was a two-way conversation, though one with extreme delays. Even at the speed of light, a signal could take hours to travel between Earth and Voyager once the spacecraft moved far enough away. Talking to Voyager was like having a conversation with an echo from yesterday, and yet the system worked. It worked so well that long after anyone expected, those faint signals still came through. Over the years, engineers performed what many called miracles. They reprogrammed software from billions of kilometers away, teaching Voyager to do things it had never been designed to do. They shut down instruments one by one to conserve power, extending the life of those that mattered most. They even adjusted how the spacecraft used its thrusters to keep its antenna pointed at Earth, despite decades of wear. With every tweak, they bought the mission a little more time, squeezing out just a bit more science from machines that should have gone silent long ago. By the 2000s, both Voyager probes had outlived not just their original mission plans, but entire generations of scientists. Many of the engineers who had launched them had retired. Some had passed away. Yet the spacecraft remained, still humming, still working, still sending back data from the deep. They had become living relics, reminders of a time when human ambition had dared to push a pair of small machines out into the infinite. For the public, it was easy to forget just how much was being accomplished by these silent travelers. Every year, Voyager's faint signals helped scientists map the edge of the solar wind, study the environment of the outer planets, and measure cosmic rays streaming in from interstellar space. The spacecraft became cultural icons featured in documentaries, films, and even science fiction stories. And of course, there was the golden record, the cosmic time capsule bolted to their sides. It contained greetings in more than 50 languages, sounds of nature from Earth, and even music ranging from Beethoven to Chuck Berry. Somewhere in the galaxy, two tiny emissaries drifted with those records attached, carrying the story of humanity to whoever or whatever might find them. Still, the heart of the mission was always scientific discovery. And as the years passed, Voyager 1 and Voyager 2 began sending back data that would overturn what we thought we knew about the outer planets. The first target was Jupiter, a massive world so enormous that more than 300 Earths could fit inside it. Telescopes had shown us bands of color, the great red spot, and a handful of moons. But telescopes couldn't capture the detail, the storms, the hidden forces at work on and around this giant. Voyager was about to change that forever. In 1979, Voyager 1 swept past Jupiter, followed by Voyager 2 a few months later. What they saw shocked scientists and captured the imagination of the entire world. It was here that the mission truly proved its worth. It was here that the story of the Voyagers shifted from a bold experiment to one of the most important scientific adventures in human history. The discoveries at Jupiter alone would have justified the entire project. But Jupiter was only the beginning. Saturn, Uranus, and Neptune still waited. And beyond them, something even more mysterious, the edge of the sun's domain itself. When Voyager 1 approached Jupiter in early 1979, no one on Earth knew exactly what to expect. Through telescopes, Jupiter appeared as a swirling marble of cream, brown, and rust, dominated by the massive oval known as the Great Red Spot. But the cameras aboard Voyager were about to bring us closer than any human eyes had ever been. As the spacecraft closed in, the blurry features sharpened into breathtaking detail, and suddenly the largest planet in the solar system came alive. The first surprise was the weather. Jupiter wasn't just a giant ball of clouds lazily drifting in space. It was a storm world, an atmosphere of chaos, filled with immense cyclones and counter-rotating bands that whipped around the planet at hundreds of kilometers per hour. Voyager's images revealed that the planet's belts and zones were more than colorful streaks. They were active weather systems, colliding, merging, and tearing apart in a constant ballet of turbulence. The Great Red Spot itself, a storm larger than Earth, was not a quiet relic as some scientists had believed, but a violent, swirling hurricane that had likely raged for centuries. And surrounding it were smaller spots, some white, some brown, all storms in their own right, surging and fading as Voyager watched. But the surprises didn't stop there. Voyager's instruments detected something extraordinary on Jupiter's night side, strange radio bursts called whistlers. These were signals caused by lightning strikes, something no one had ever observed beyond Earth. Then the cameras caught faint flashes within the clouds themselves, bolts of lightning ripping through Jupiter's dark skies, illuminating vast storm systems from within. For the first time, humanity had proof that electrical storms weren't unique to our own planet. They were part of the universal language of weather. Then came the discovery that stunned everyone. On March 1979, Voyager 1's camera captured an eruption on Io, one of Jupiter's innermost moons. What looked at first like an odd arc or smudge near the moon's edge turned out to be a volcanic plume, sulfur dioxide blasting hundreds of kilometers into space. This was history in the making. No one had ever seen active volcanoes anywhere but Earth, and suddenly, here was Io, not just a dead frozen rock, but a violently active world reshaped every day by fire and sulfur. Voyager's images revealed multiple plumes, some towering so high they curved back down under the moon's weak gravity. Lava lakes bubbled on the surface, and rivers of molten rock carved new paths across the tortured landscape. Io wasn't just alive. It was the most volcanically active body in the entire solar system. As if that weren't enough, Voyager also changed our understanding of Jupiter itself. Until then, Saturn had been thought of as the ringed planet, the only world with such a majestic feature. But Voyager's sensitive instruments and cameras revealed a faint, dusty ring encircling Jupiter as well. It wasn't bright and obvious like Saturn's, but it was there, thin, delicate, and made of fine particles kicked up by micrometeoroid impacts on the planet's tiny moons. This discovery meant that ring systems weren't rare at all. They might even be common among the gas giants. And speaking of moons, Jupiter's family grew larger thanks to Voyager. 2 tiny new moons, later named Thebe and Metis, were spotted for the first time, joining the already impressive collection. Each one was small and irregular, more like captured asteroids than proper moons, but they added to the complexity of Jupiter's system and hinted at a chaotic history of collisions and captures. Voyager's instruments also mapped Jupiter's magnetosphere, the invisible bubble of charged particles and magnetic fields that surrounds the planet. What they found was shocking. Jupiter's magnetic field wasn't just strong. It was monstrous. It dwarfed Earth's by orders of magnitude, stretching millions of kilometers into space. Trapped within it were belts of radiation so intense that they could fry unprotected spacecraft electronics in hours. Any future missions would have to contend with this dangerous environment, but for scientists, it was a thrilling revelation. Jupiter wasn't just massive in size. It was massive in influence, shaping the space around it in ways we had never imagined. And then there were the moons, the Galilean moons, discovered by Galileo himself centuries earlier, but now seen up close for the very first time. Europa was perhaps the most haunting. At first glance, it appeared smooth and pale, its surface crisscrossed with dark cracks. But those cracks hinted at something profound, an ocean of liquid water hidden beneath the icy shell. Could Europa be hiding a warm, salty sea beneath its frozen surface, perhaps even an environment where life might exist? Voyager's data raised questions that still fuel missions today. Next came Ganymede, the largest moon in the solar system, bigger even than the planet Mercury. Voyager revealed a surface split between ancient cratered regions and newer grooved terrain, evidence of geological activity that had reshaped parts of the moon over time. Callisto followed, a world battered beyond recognition, its surface scarred with craters upon craters, frozen in time as a record of the solar system's violent past. Finally, Voyager gave us our first real look at Amalthea, an oddly shaped reddish moon that tumbled through its orbit like a lopsided rock, a stark contrast to the giant spheres around it. Together, these moons transformed our understanding of planetary systems. They weren't just lifeless rocks circling a gas giant. They were dynamic worlds, each with its own story, its own mysteries, and in some cases the tantalizing possibility of life. Voyager had turned Jupiter from a distant dot in the sky into an entire miniature solar system of storms, volcanoes, oceans, and frozen time capsules. When the Voyager team looked back at all they had learned from this one encounter, it was overwhelming. They had discovered lightning beyond Earth. They had seen volcanoes erupting on another world. They had found new moons, new rings, and clues that icy oceans might exist on faraway worlds. In less than a year, Voyager had rewritten everything we thought we knew about Jupiter, and yet this was only the first stop. Ahead lay Saturn, with its dazzling rings and mysterious moons, waiting to reveal secrets just as strange, just as profound. When Voyager turned its gaze toward Saturn, expectations were sky high. Saturn had always been a showpiece of the night sky, its dazzling rings admired through telescopes for centuries. But no one knew the details, the textures, the hidden secrets that only a close-up look could reveal. As Voyager approached, the planet resolved into a golden sphere wrapped in delicate bands of cloud, majestic and mysterious, and its rings, those thin arcs of brilliance, spread out like a cosmic masterpiece. The first thing Voyager revealed was just how intricate those rings really were. From Earth, they looked like a few wide bands, almost solid in appearance. But up close, they dissolved into countless narrow ringlets, each made of ice and rock fragments ranging from tiny grains to house-sized boulders. It was a dance of particles, orbiting in delicate balance, sculpted by gravity. Voyager's instruments discovered strange, dark spokes gliding across the rings, as if painted shadows were drifting through the icy arcs. No one had ever seen anything like it, and to this day, the exact mechanism remains partly mysterious, though scientists suspect magnetic fields play a role. Saturn's moons also came into focus, and with them, some of the most astonishing worlds in the solar system. Titan, Saturn's largest moon, loomed as the crown jewel. Voyager's instruments confirmed that Titan had a thick atmosphere, denser than Earth's, shrouding the surface in an orange haze. At the time, scientists couldn't see through it, but they knew the atmosphere was rich in organic molecules, the chemical building blocks of life. It was a tantalizing discovery, one that would inspire future missions like Cassini and Huygens to dig deeper into Titan's mysteries. Then there was Enceladus, a small icy moon that Voyager revealed as brighter than fresh snow, reflecting nearly all the sunlight that struck it. At first, it seemed like a frozen wasteland, but Voyager's data hinted at something unusual, a surface that was smoother and younger than expected, suggesting hidden forces at work beneath the ice. Decades later, we would learn that Enceladus is home to geysers blasting water into space from an underground ocean. Voyager had given us the first hints of this possibility, even if we didn't recognize it at the time. Other moons added their own flavor to the story. Mimas, with its enormous Herschel crater, looked like a giant eyeball staring back at the spacecraft. Tethys and Dione showed signs of ancient fractures like scars left from cosmic collisions. Rhea appeared heavily cratered and old, while Iapetus stunned scientists with its two-toned surface, one hemisphere bright as snow, the other as dark as coal, a mystery that would puzzle researchers for years. Voyager revealed each moon as a character in its own right, no longer just points of light but worlds with identities and secrets. As with Jupiter, Saturn's magnetosphere turned out to be vast and powerful. Voyager mapped its extent and revealed a system alive with charged particles and magnetic storms. But it was the rings and moons that captured the imagination most. Saturn, more than any other planet, embodied beauty, complexity, and wonder all at once. After Voyager 1's encounter with Saturn in late 1980, mission planners faced a choice. The spacecraft had the trajectory to swing toward Pluto, but only if it skipped a close encounter with Titan. Because Titan's thick atmosphere was too compelling to ignore, Voyager 1 was directed past Titan, sacrificing the Pluto flyby but giving humanity its first close look at this mysterious world. Voyager 2, meanwhile, was sent on toward Uranus and Neptune, ensuring that at least one spacecraft would complete the grand tour. By the early 1980s, Voyager had already exceeded all expectations. What had begun as a 5-year mission to Jupiter and Saturn had become a decades-long odyssey that would reach the very edge of the solar system. Even after leaving the giant planets behind, Voyager's instruments continued to function, sending back data about the outer solar system, the solar wind, and the far-off frontier where our star's influence fades into interstellar space. And then there was the golden record, a time capsule of humanity bolted to the side of each spacecraft. On it were greetings in dozens of languages, music from cultures across the world, sounds of Earth like birdsong, thunder, and laughter, and even images encoded in analog form, showing what our world looks like, what we eat, how we live. It was humanity's message in a bottle, cast into the cosmic ocean, in case someday, somewhere, someone, or something might find it. The Voyagers weren't just scientific missions. They were ambassadors, carrying a piece of all of us into eternity. As the decades passed, both Voyagers continued their journey outward. Voyager 2 went on to become the only spacecraft ever to visit Uranus and Neptune, revealing the pale blue worlds and their moons in stunning detail. Voyager 1, meanwhile, headed on a trajectory that would eventually carry it out of the solar system entirely. In 2012, Voyager 1 crossed the heliopause, the boundary where the solar wind gives way to interstellar space, making it the first human-made object to leave the bubble of our sun. Voyager 2 followed in 2018, crossing the same threshold. Even now, billions of kilometers away, both spacecraft still whisper faint signals back to Earth, their power dwindling but their legacy eternal. Looking back, the story of Voyager is more than just a chronicle of scientific discovery. It's a testament to human curiosity, ingenuity, and the desire to reach beyond what we know. From the storm-racked clouds of Jupiter to the icy moons of Saturn, from the discovery of volcanoes on Io to the hints of hidden oceans on Europa and Enceladus, Voyager reshaped our understanding of the solar system. It showed us that the planets and moons are not static relics but dynamic, evolving worlds, some with the potential to harbor life. But perhaps the most profound legacy of Voyager is the perspective it gave us on ourselves. In 1990, long after its planetary encounters were done, Voyager 1 turned its camera back toward Earth at the request of Carl Sagan. From a distance of 6 billion kilometers, our planet appeared as a pale blue dot, a speck suspended in a sunbeam, almost lost against the vastness of space. That image reminded us of our fragility, our unity, and our place in the cosmos. Everything we have ever known, everyone who has ever lived, existed on that tiny mote of dust. The Voyagers, in their silence, gave us not only knowledge of other worlds, but a deeper appreciation of our own. Today, both spacecraft continue their long, slow voyage into the interstellar night. Their signals grow fainter, their instruments gradually shutting down as power runs out, but their mission is not over. They will keep traveling silent and unobserved for billions of years, long after Earth itself has changed beyond recognition. Somewhere out there, the golden records will continue to spin, waiting for a finder who may never come. Yet even if no one ever hears them, they remain a message of hope, proof that once upon a time, on a small blue world, a species dared to dream of the stars.